कम लग रहा है। नहीं कल नहीं रखूँगा मैं फिर इसीलिए, क्योंकि देयर इज़ फिर मेरी आफ्टरनून में एक क्लास और है, सो दैट्स वाई, सो वो तो मुझे लेनी पड़ेगी क्योंकि, तो कल नहीं रखेंगे हम। आज थोड़ा खींच देते हैं, अगर आज आधा घंटा खींच गया और एक दिन और थोड़ा और खींच गया तो बराबर हो जाएगा ना फिर। आई डोंट नो, इज इट ओके इफ आई गो, यू हैव अ क्लास एट 1 और समथिंग, या मतलब लंच 2 बजे तक होता है, तो अगर इफ वी गो टिल अबाउट 1:20, so that we can do for 2 or 3 days, so that will take care. Already we have done that once or twice before. To यहाँ नहीं रहा क्या? आ गया, ठीक है। So this is where we were at the end of last class. We talked of the 3 flows. I don't know, तुमने lecture देखा कि नहीं? You were not there in the last class, ना? कि थे? तो well, I'll start from here. But the 2 options you have, well, we have already circulated the list for video lectures also, and the lectures were uploaded immediately. Almost are being uploaded on the same day. So even if you miss a class, please try to, because otherwise you will not find anything. So this is now we are talking of these flows, the jet, shear layers and wakes, and what we found was in a wake there are 2 velocity scales, u0 and us. The gap, basically the defect is u0 minus u at the center line is us. That is what we called. So that is one of the things, that is one defect, one velocity scale, and u0 the velocity scale is the, in other 2 flows, the shear layers and the jets, there is only one velocity scale, us, and those were defined in the figure in the last class. And then we were trying to look at the equations. So we were looking at the equations for a 2-dimensional flow which was slowly evolving, which meant that partial by partial x of all statistical quantities was much less than partial by partial y. So we started with du by dx, and we said that wherever u is varying, then the variation will scale with us, not with u0, because u0 can change independently of us. And then some very good questions were asked. I think one of you asked, what is the role of the jet origin? Because the equations did not contain anything in the origin. And some of those answers will come out as we do the analysis. So some very good questions were asked. What is the role of the origin of the jet? If there is a very strong jet vis-a-vis a weak jet, what is the difference? The equations don't seem to show that at all. Yeah?
Like if we do scale analysis.
Yes.
So for the 3 flows, when we do del by del x.
Yes.
So will it be us or it will change for wave?
So that is what we have done. We have defined it as wherever the derivative comes, it will be u0 minus us, or us basically. But if the term u comes alone, then we make it u0. But then in the wake, u0 is there. In the other flows, u0 is not there. So therefore that term will go away. So we will have only 2 terms in one of the equation and 3 terms in the other. That we are coming to. Anyway, let me. So what we have, our whole idea was, first we looked at the order of magnitude of various terms. Order of magnitude of mean u, order of magnitude of mean v, order of magnitude of x, order of magnitude of y. And then we have a mu. So these are the order of magnitudes we have looked upon. And to get the order of magnitude of v, we did not know what is the order of magnitude of v, because the flow, if you look at the physical parameters in the flow, there is only vx, there is no vy. So vy is coming because of the flow. So the order of magnitude also has to come from the equations. and that is why we use the continuity equation to get the order of magnitude of V.
Sir, so can we use instead of US that you have mentioned like then u of tilde? So we can write.
No, so if you use u of tilde here, see what was u of tilde? It was either u0 or us. So now if you use u0, then that is not correct, because in a wake, what is varying? See, wake flow is something like this. So this is u0 and this was us. Okay? So now when we talk of variation, then the variation is of u0 minus u, which is us. So for variation, us will become the right scale, not u0, because this u0 can change. We can change u0, us will also change because of u0 changing, but the variations will scale with us, not with u0. See, the reason why we are doing all this is like in this way is to just so that one analysis takes care of all three. But then as you will see, we will look at the separate equations for each of these quantities. So maybe instead of doing this, I could have just said wakes first, then jets, then shear layers. But again, a lot of this I am doing it so that to keep consistency with the book, because that is what you will read eventually. So from here, we first got the order of magnitude of V, and this is the same exercise which we do when we do boundary layer flows. In boundary layers, if you look at laminar boundary layers, this is the order of magnitude analysis we do. It is very similar to that. Then we went, and as we do in boundary layers, we went to the Y equation. And from Y equation, what we got was that partial P by partial Y was equal to the biggest scale, which was by itself very small. So therefore, this was equal to 0. That is what we got here. That so I don't think I've done that. Let me just see where I am in the lectures. So okay. So now I have to do. So at the end of last class, we had gone to the equation of V. I had not done the order of magnitude analysis. I will start from here now. Okay. So today's lecture will start from here. I'll when we do laminar flow analysis, a lot of these terms are actually 0. But here now we will have to resort to an order of magnitude analysis, and let us see now. So the first term we look at is mean of u dV by dx. So this will be equal to u hat upon L US times small l upon L. The order of magnitude of u, this is without a derivative, so this will be u hat. D by dx is L, and the order of magnitude of v is US times L upon L. So, this is the order of magnitude of the first term. The second term, and what we do is this, we will write it as, and there is a reason why we are doing it, we will write it as u hat upon u prime RMS, US upon u prime RMS times L upon L whole square u prime RMS square upon small l. So, of course, all I am doing is multiplying and dividing by constants. So, I am making the non-dimensionalization factor of u as u prime RMS, which is a scale turbulence velocity scale. So, US also I do the same thing. So, I get u prime RMS whole square, which comes here, and then there is a small l upon capital L square. So, I have multiplied by small n and divided by small n. And the purpose of this analysis is, in all these terms I will keep u prime RMS square upon L and look at the factor in front of these, and then decide whether it is big or small and how to tackle that. So, this is the first term. The second term is mean of v dv by dy. So, this is of the order of, now what is the order of magnitude of v? V is equal to US times L upon L, there is a v square into 1 over small l. Okay, because v is of this order, there is a v square, and d by dy means 1 over L, the cross derivative. So, this again will become US upon u prime RMS whole square times L upon L square times u prime RMS square upon small l. This is the order of magnitude of the second term. The third term is partial by partial x of u prime v prime. Now, u prime v prime we said were of order of what? U prime RMS. So, this will become u prime RMS square divided by capital L. So, this is of the order of u prime RMS square upon capital L, and this can be written as L by L times u prime RMS square upon small l. The fourth term is partial by partial y of v prime square. So, this will be of the order of u prime RMS square upon small l. And this was the reason, because this turns out to be the biggest term. So, we are taking this out as common and comparing all the coefficients with respect to this. Then we have the fifth term, and for the pressure term, it always is the case that we balance it with the remaining terms, because here we do not, unless if we know what the pressure is like. So, since we do not know this, so this we keep as the scale which will be balancing with the biggest term otherwise. Now, the sixth term is nu times d2v by dx square. So, this will become nu times US times L upon L into 1 upon capital L square. Nu again simple, v is of the order of US L upon L, and then 1 over x square. So, 1 over capital L square. So, this once we Now, reworded, this will become equal to US upon U prime RMS. There is a nu, so we make 1 over RE sub L, and then what we will find is this becomes L by L cube times U prime RMS square upon small l. Now, RE sub L so nu, if you have nu, you can replace it by U prime RMS times small l divided by RE sub L, and that's how we get this term.
So,
Yeah.
while doing this differentiation, like del 2 of v by del x 2, so the interpretation for this would be that we are giving an order of term for x to be L. My question is that we have to choose a characteristic length for the v motion of the particle. So why is that L? So L is the characteristic motion for the u motion, right? But
No, see, it is again there is a d2v by dx square, d2v by dy square. So now, if you look at d2v by dx square, let's try to see what is that. That will be, if you look at it in terms of a grid or a numerical simulation, then the second derivative is equal to v at n plus 1 minus v at n minus 1 divided by delta x square. So, on the top you will get the differences in v. So, therefore, we use the order of magnitude of v, and in the bottom what you get is delta x square. So, therefore, these grids have to be scaled with delta x, which is in L, and if you compare it with d2v by dy square, which is the next term which we will do, then instead of this delta x square you will get delta y square. So, then the delta y has to be within those grids, within that small y. So, that is why.
it is a matter of consistent modeling.
Yeah, it's a matter, we are trying to just see the order of each of these terms, and anyway eventually this will not matter, because when we go in the limit Reynolds number being high, we will then all these terms will become 0. But within these two terms, again it so happens that it's the x derivative which is lesser than the y derivative, if everything else is the same. The same thing doesn't happen in the continuity equation. See, in the continuity equation also you have du by dx and dv by dy. So, one may feel that the d by dx term will be much less than the d by dy term, but then there is on the top there is a u and there is a v, and the v term itself scales because of the continuity equation like very small. So, that is why in the continuity equation both the terms are of the, or in the left hand side both the terms are of the same order, but on the right hand side, because everything else is the same, so therefore the x derivative term will be much slower or much smaller compared to the y derivative. Then we have the final term which is equal to nu times d2v by dy square. This will be of the order of nu times USL upon L, this is order of v, times 1 upon small l square, and this one can write it as US upon U prime RMS times 1 over RE sub L, and now we will get, instead of L by L cube, we will get L by L times U prime RMS square upon small l. Now, when we look at various terms, since we are talking of turbulent flows, RE sub L is large. And also we will talk when we go sufficient downstream, then we will expect L by L to become smaller and smaller. We have not shown this, but this we will show, but REL is large. Now, if REL is large and then U prime RMS is of the same order as US, so then what we find is that the terms 6 and 7 are small as compared to 4 because RE sub L is large. We look at 6 and 7 and 4. 4 is only U prime RMS square upon L. 6 and 7 have something else multiplied by 1 over REL. Okay. And if unless U prime RMS square upon U hat times US goes to 0 as fast as L upon L square, unless this happens, the terms 1, 2 and 3 are negligible compared to 4. Now, once again let us see what is 4. I will bring it down again. 4 is U prime RMS square upon L. 1, 2, 3 have got one of the terms as U hat upon U prime RMS. US is of the same order, so we get it like this, and then there is a L by L square, which again we expect to be going small. So, therefore, these first 3 terms also will be less than U prime RMS square upon L. Yeah. See, now the first term is what? So, there we have, that is why we have put the condition, this U hat upon U prime RMS, this can be large, because so that means unless if this product is of order 1, if this is small also, so that is a condition which we are imposing, there is a L upon L whole square and there is a U hat upon U prime RMS, US upon U prime RMS. This will be probably of order 1. Now, this can be large, but then, so unless if this times L upon L square is of order 1, so we are saying, and if this is not of order 1, this is less, then we have only the other 2 terms. This could be depending on the value of U0. See, again only for wake this will matter. For this will not matter for jets and shear layers because U hat is 0. So, that means we are imposing an additional condition on jets, on wakes, that this term has to be less than order 1. Okay. So, and that is what is specified by writing here, unless if this tends to 0. So, now I have inverted it, so that is why then I say this goes to 0. So, if this happens, then what you get is partial V prime square by partial y is equal to minus 1 over rho dp by dy. And let me call this equation A, and this is valid if the only condition which we U hat upon U prime RMS times US upon U prime RMS times L upon L whole square goes to 0, and the second condition is US upon U prime RMS times 1 over RE This term is the coefficient of the x derivative u du by dx. This term is the coefficient of d2v by dy square, nu d2v by, whenever a Re comes, that means there is a nu. So this is the viscous, dominant viscous term, and this is the dominant x momentum term, or the not x momentum term. So if these two terms go to 0, so we put this condition, and to impose these conditions, we impose the limit L by L goes to 0, so that above two conditions are satisfied. And later we will show that L by L tends to 0 if REL is large. So right now we are proceeding with the analysis assuming small l by capital L goes to 0. So then what we do is we integrate the equation A with respect to y. Equation A is what? Partial v prime square by partial y is equal to minus 1 over rho dp by dy. So when we integrate this, what we get is partial p by partial rho plus v prime square is equal to p0 upon rho, where p0 is the pressure outside the turbulent field, which means y tends to. So P0 is the pressure at infinity where V prime is 0. So V prime value here will be 0, so pressure will become P0. So at infinity, this is what the pressure is, P0. So we get, see, the equation was partial P by partial Y, 1 over rho. We assuming rho is constant, it's incompressible flow. So this becomes P by rho. Integral of V prime square with respect to Y will give us V square. It actually becomes a function of X, but then we are assuming then that at infinity the pressure is not a function of X. So P0 is outside the turbulent this thing.
So can we really say that V prime is 0 at infinity?
Yeah, at infinity, because see what is happening is we are talking of this jet flow. So basically the turbulence part is confined within this wake zone. So once you go very far in the wake flow, then V prime is 0. Similarly in the jet flow, the jet is coming out from here. So this is expanding like this. So once you are integrating like this, this is your jet. So beyond this region there is no turbulence. In fact, probably everything is the same as the laminar velocity, which may be 0. So not even just the prime, even V itself will be 0. Okay. So this is the equation which we have. Now this equation B, this holds for narrow slowly evolving flows. Slowly evolving flows will mean the L dimension is much less than capital L. It's basically and this holds if P0 is not a function of X, and this we will assume that at infinity the pressure, or at far away the pressure is not changing with X. That means there is nothing else in the flow. Suppose if there was some other source at infinity or far away, there is something else which is causing a pressure gradient, then these equations will not be valid. So this is for a case like this where there is no flow. if dp0 by dx is not equal to 0, we really cannot even say that d by dx will go like 1 over L, because dp0 by dx will give another length scale in x. If pressure is also changing with x far away, then that change will give us another length scale. So, then we just cannot talk about it like this. So, now we also differentiate the equation B. What was the equation B? The equation we got for pressure with respect to x. And this we do because we will need this equation in the x momentum equation, 1 over rho dp by dx plus partial v prime square by partial x is equal to 0. And if you now try to see, this is exactly what we also do in laminar flow analysis in laminar boundary layers. What do? We first, there of course what we get is partial p by partial y is 0. And then we come to the x momentum equation. In the x momentum equation, we change partial p by partial x to dp by dx. And in flows where capital U is constant, we say dp by dx becomes 0. Now, here because of the Reynolds stress terms, dp by dx becomes equal to minus of partial v prime square by partial x multiplied by rho. So, analysis is very similar the way we are doing it, but obviously terms are more involved here. So, once we do this, then we move to the x momentum equation, and we will do the same things with the x momentum equation. And the whole purpose of doing all that with the y equation was to get an expression for partial p by partial x in terms of velocities and Reynolds stresses. So, that is what we have been able to do from the y momentum equation. So, now when I go to the x momentum equation for mean velocity, this is equal to, first let me write the full equation, u du by dx plus mean v du by dy plus d by dx of, now I will get u prime square. Then there is a minus dp by this, I also put this term comes from dp by dx, and then there is plus d by dy of u prime v prime. This is equal to nu times now. This sort of equations, given these conditions, you should be able to derive for simple flows. Suppose if I give you a condition that there is a two-dimensional flow, I will also talk of axisymmetric flows a bit later. So, what simplifications do we make there? So, then given the general mean equation, you should be able to write firstly these forms, one for the y equation, and then do some analysis like what we have done to simplify the y equation, and then get to the x equation. Maybe I will give you a similar problem in the homework as the 4th or 5th homework, so that you can do these analysis there.
Why is this term coming with the negative sign?
Because on this was minus 1 over rho dp by dx, and minus 1 over rho dp by dx we showed was equal to partial v prime square by partial x. Yeah, just here. So, we have just took it, there are two things we have done. We have just, this is this term. So, I have taken it on the other side. So, it becomes, so this is, see here in the left hand side it was minus 1 over rho. Huh?
and then we take it
Huh?
to LHS.
Yes. That's right. Then we take it to the LHS. So now basically this equation contains only mean u, mean v and Reynolds stresses. U prime square, v prime square, u prime, v prime. Pressure has been thrown away. That is the sort of crux or the physical crux which we have in these terms. Okay. So now once again we do a similar analysis like what we have done earlier for the V equation. Are you people with me? बहुत अलग तो I think we are doing things at a slow pace, and so now once again I will move with the same thing. Mean of u du by dx, this will be equal to order of magnitude of u times us upon L, and this I will write it as u hat upon u prime RMS us upon u prime RMS times L upon L times u prime RMS square upon small l. So now I will compare everything with respect to u prime RMS square upon small l. Now what will be the order of magnitude of the second term? V du by dy, and this we should expect will always give us the same thing. The only thing was that instead of u hat we will get, so V will be equal to us times L upon L, and du by dy will be us upon small l. So this again I can write it as us square upon u prime RMS square times L upon L u prime RMS square upon small l. Okay. For the third term I take partial by partial x of u prime square minus v prime square. I take both of them because they are of the same order. This will be equal to of the order of u prime RMS square upon capital L. So this I can write it as L by L u prime RMS square upon small l. Then I have the fourth term, what is the order of magnitude of this? Small l, u prime RMS square upon small l, and this becomes therefore the major term. This is of the order of u prime RMS square upon small l, and so I do not need to do anything. This is equal to u prime RMS square upon small l. Now the fifth and the sixth term, let us see, one is nu times d2u by dx square. This is of the order of nu times us upon L square, and this I can write it as us upon u prime RMS is a nu, so I get REL times L upon L square times u prime RMS square upon small l. These viscous terms you can probably check at home wherever there is a nu. So we have to convert it in terms of RE sub L, and we get it in this form. And the sixth term, nu times d2u by dy square. Now this of course will be a different order, nu times us upon, using my boundary layer is in my head, so I was writing delta, but it is actually of ul square. So this becomes equal to us upon u prime RMS, nu becomes 1 over REL times u prime RMS square upon small l. Now, if REL is large, 5 and 6 will go to 0. We'll probably have a look more at all these terms, but u prime RMS and US are of the same order. And in the second term, 1 over REL is small, L upon L square is also very small. So, therefore, this will be 0. Now, what about 3? So, we have total 6 terms. Fourth term is u prime RMS square upon L. 5 and 6 are very small because of RE being large. Now, in this term it is L upon L times u prime RMS upon L. So, that will be small. Again this term seems to be small, it is L upon L whole square. L upon L times these are of the same order. So, that means if term 4 has to be balanced, then I have only the first term which is there. So, for the first term to be balanced, this quantity should be of order 1. Okay. So, let us write this down. So, let me put all these arguments which I have just said. If REL is large, then 5 and 6 are small. L by L tends to 0, then 3 is also negligible. So, to balance 4, which is d by dy of u prime v prime, one more term is needed, at least one more term is needed. If u hat is bigger than US, then we require u hat upon u prime RMS, US upon u prime RMS times L upon L is of order 1. This is what we will require. So, now let us talk of the 3 different type of flows and see what happens. So, first let us talk of wakes. In wakes, there are 2 ways to satisfy, sorry, हाँ चलो पहले 1 मिनट लिख लो इसको अच्छी तरह.
To have a balanced x momentum equation, this is a requirement, right?
We are saying that this, otherwise that term itself will also become very small. Then every term is of order 0. That could also happen, that see, unless if this term is of order 1, then the 2 terms will balance out. Otherwise, if this is also very small, then the conclusion you get is that term 4 also has to be of order of all these other terms, which is very small.
But so, if this is true,
Yeah.
this is tending towards order 1, so that this is not
So, now there are 2 terms.
So, the y momentum equation that we wrote, in
Huh.
that a third term will also come, right? Because this is the same thing that we assume to be very small when we were
Is it?
writing
I
y.
don't think so. Let me just see. I think there was a L by L square. Let's just see. Similar थी, but ये नहीं होगी same. उसमें एक L by L extra होगा. It was L by L square, I think. It was an L by L square. See, that always happens because the y momentum equation, again, if you just try to think about it in terms of laminar boundary layer, the y momentum equations are always have one order less than the x momentum equations. That's why I was so confidently saying it has to be less. That was the reason for my confidence, otherwise I would also. So now let's try to see what are the implications of this. So we are saying u prime u hat upon u prime RMS times us upon u prime RMS times L by L is of order 1. So now if u prime RMS upon us, this is of order 1, and this one expects, because whatever is the variation in the wake, that is of the order of the turbulent velocity. This us you expect it to be of the order of u prime RMS. So if that is so, then what it tells you is, this implies that u prime RMS upon u hat, this is of the order of L by L. And this is the situation which happens in, that means what you are saying is that for this to be valid, the turbulent velocity vis-a-vis u hat, which is the u0, this has to be of the same order as small l upon capital L. Now, when the wake is downstream, L is small. So that means you are expecting the turbulence intensity also to go down as as x increases. So that is what you are expecting here, and this is a condition when the equation will be valid. And this is a situation in far wakes. The turbulence intensity is of the order of the, this is the first condition, u prime upon u RMS and us are of the same value, turbulence intensity of the sort, and both are small with respect to u0. So as the wake evolves, अभी बताता हूँ क्या चीज, सिचुएशन इन फार, एक मिनट इसको तो, in far wakes, turbulence intensity is of the order of velocity defect. There is nothing there. So now, because u prime RMS is of the order of us, this implies T2, or that, what did I write it? I wrote it as circle. Huh? This will imply that two is negligible. So the equation for wake becomes capital U du by dx plus d by dy of u prime v prime is equal to 0. Mean of u is, this u tilde is of the order of u0, u prime is of the order of us, and if we look at mean of u minus u 0 divided by u 0, this will be of the order of us upon u 0, which is of the order of small l upon capital L. So, what we also do is in this equation, the mean of u, the undifferentiated term, can be replaced by u 0. Wherever of course, it is differentiated, we cannot do that, but the undifferentiated u here, we can replace it by u 0. So, if we do that, the equation becomes u 0 d mean of u by dx plus d by dy of u prime v prime is equal to 0. And this equation tells you that the net momentum flux due to cross stream velocity fluctuations v, which is basically v prime, is replaced by x momentum carried by mean flow in the streamwise direction. So, what you are saying is there is this term d by dy of u prime v prime, which represents the momentum flux due to v prime. See, v prime is the vertical velocity fluctuations, and there is a momentum flux due to this. This momentum flux is replaced. So, whatever is happening in this y direction momentum, this is replaced by the mean momentum in the x direction. That is what this equation physically tells you, that the momentum flux of the y fluctuations is being replaced by x momentum. Okay. Now, once again the conditions which we had for this. So, one condition, कहाँ से आ गया ये? Sorry. So, the condition we had was u hat upon u prime RMS times us upon u prime RMS times L upon L whole square. This goes to 0, and us upon u prime RMS into 1 over REL times L upon L goes to 0. Now, let us say this is C1, this is C2. C1 satisfied if L upon L goes to 0 and u prime RMS is of the order of US, and C2 is satisfied if L upon L times 1 over REL tends to 0. Now, obviously, the second condition is very easy to meet because REL is large and L upon L is also small. So, therefore, C2 is easy to meet and C compared to C1, but if these conditions are met, we get this equation for the wake. And what is our equation for the wake? The equation for the wake is u0 du by dx plus d by dy of u prime y prime if v prime is equal to 0. So, this is for wake. Next, we look at the case for उसकी क्लास थी क्या हर्षल की? His bag is still there. अच्छा, we'll come there. Now, in jet set mixing layers, we don't have U0 and U hat is just equal to US. There is no this thing. So, now when we put in the condition U hat upon U prime RMS times US upon U prime RMS times L upon L is of order 1. So, this leads to U prime RMS upon capital US whole square is of order small l upon capital L, and we get a different condition now U prime RMS upon US, this is of order L by L to the power half. Earlier we got the condition U prime RMS upon U0 was of the order of L by L, isn't it? We got U prime RMS upon U hat was of order L by L. Now what we get is U prime, because now there is no U0. So we have to scale things in terms of US, and what we get is U prime RMS upon US is of order L by L for this analysis to be valid, which means that now U prime RMS and US will not be of the same order. Earlier they were of order 1, that's what we said. But now U prime, because in these flows, in jets and all, if you look at it, this is what is US or some centerline velocity somewhere in the center. This is of the order of US. So now all the fluctuations are within this. So these fluctuations are less than US. Whereas in the wake, the fluctuations were within this region and this US was also of the same order. So therefore, U prime was of the same order as US. But in this flow now, this whole flow, the mean U is also of this order. So the fluctuations are less than this. So if you look at the two flows also, it seems to make sense. But then when we look at now the X momentum equation for jets and wakes, now both the terms will stay valid. We get mean of U du by dx plus mean of V du by dy plus d by dy of U prime V prime is equal to 0. Earlier we got U0 hat du hat by dx plus d by dy of U prime V prime is equal to 0. Now both the terms which are there, the convective terms, both of them are of the same order, because there is no u0, it's only us square which comes in. So therefore, the equation now contains 3 terms. This is the x momentum equation for jets and shear layers, and here the condition, the physical interpretation becomes that the x momentum removed by v prime fluctuations, which is basically the third term, is replaced by both downstream and cross stream components of mean velocity. So, as I told you, let's go on for about 10 minutes more, if you people permit me. So then if I do that 1 or 2 days, then I don't need to call the extra class. So that's what I'm going to do. I'll just continue for some more time. So now here again we are going back to the same exercise, writing the x momentum equation, but now for jets and shear layers. And what we find is we get this equation. Now we will have to look at the conditions again, because now u hat is not equal to u0. So now we have to re-examine the two conditions which were there. So the first term condition was u hat upon u prime RMS times us upon u prime RMS times L upon L whole square goes to 0. This will hold if now u hat is u prime is us. So this will hold if u prime RMS upon us is of order L by L to the power half. And we have us upon u prime RMS times 1 over REL times L upon L. This goes to 0. So this us upon u prime RMS, we will put it as equal to L upon L to the power half into 1 over REL tends to 0. So these are the two conditions we get, and now for neglecting the viscous term, we get a more stringent condition. For neglecting viscous term, we have us upon u prime RMS into 1 over REL must tend to 0. Now us upon u prime RMS will become capital L by L to the power of half into 1 over REL must tend to 0. So this means that REL must be large enough, because now 1 over REL, which is a small term, is being multiplied by capital L upon small l, which is large. So, therefore, REL has to be sufficiently larger compared to this order, so that this term can go to 0, and what we get is on this REL we get a condition that REL must be large enough. That means it should be of the order of L by L to the power of 3 by 2. The one more order, exactly. So, there should be one more order for this to happen. And which was the equation double star, there was a double star equation. So, that means for the momentum equation, mean of u du by dx plus mean of v du by dy for this equation to be valid, L by L must go to 0 and capital L by L to the power of half times REL to the power of minus 1 should go to 0. So, these two conditions must happen. Now, what one finds is that the only way to check this is from experiments, and what we find is for wakes L by L decreases as we go downstream. But this condition we are putting is for shear layers. So, equation for wake is a good approximation. However, for jets and mixing layers, L by L tends to a constant, but does not go down as we go with x. It tends to become a constant. But the good part or the lucky part of this is that this constant is small. This is something like of the order of 6 into 10 to the power of minus 2. So, this implies that the neglected terms are about 6% of the retained terms. So, for each flow which you encounter, you have to look at the REL and look at small l upon L, how they change downstream, and then decide whether you can make approximations like this or not. So, each type of flow will have its own regimes, and this is what one of the take home lessons for us is, that while we are doing these approximations, but we have to look at the order of magnitude of each of these terms to be able to move ahead. Now, the next topic I will do in the next class, because it will take me some time, I do not think. But the next topic which we will cover here is the momentum integral for these flows. So, what we will do is we will be looking at the x momentum equation, integrating them, and then we will be able to show that we get a constant which is related to the flow, and that will answer the question which was posed as to what happens with different type of jets, with different wakes. If the flow strength is different, that difference shows up in a constant which will come up as a momentum integral, which we will see in the next class. Okay. So,